Hello, this is solving the Laplace equation part 2 in spherical coordinates. So at the end of part 1, we got this beautiful differential equation which incorporated the angular part in spherical coordinates, and I said that the solution was the Legendre polynomials, which you could just plug into that equation and they would work. So we want to prove that this is in fact the solution to this differential equation. So to do this, we are going to start by doing something weird, right? So these are one of these differential equations, the pain to have to go through. So we're going to start by defining some variable we call v, right? And we're going to say v is equal to x squared minus 2 to the nth power. Okay. And then what we're going to do with this, which is kind of like something super interesting, we're going to take the following quantity. We're going to go x squared minus 1 times dv dx. All right. Now, let's go ahead and prove this out, what this is going to be. We're going to have x squared minus 1, and we're going to have d dx, x squared minus 1 to the nth power. We're going to have to use the chain rule. So this is going to become times L, x squared minus 1 to the L minus 1 power. Right? But I'm going to go, times 2x, right? Because I have to do the derivative inside the chain rule part. So now what I'm going to do is multiply this through. Well, if I take x minus 1 times x squared minus 1 to the L minus 1 power, that's just going to make this to the nth power. So this becomes 2lx x squared minus 1 to the nth power. But hey, I already know what that is, right? That is going to be up there. We're going to have 2lx times v. That's a pretty nifty little thing, right? And now we're going to do something super wacky. We're going to go ahead and we're going to take the derivative, but we're going to take the L plus 1 derivative of that equation. That's a weird, wacky thing to do. But hang out with me. We'll get there. All right, so if I take this derivative, right? So if I take the first derivative of this, then I have to use the product rule, right? You're going to have dlv plus dlx v prime, right? Oh, sorry. Okay. Now, if I do it yet again, I take another one of those derivatives, you get again, when I take the derivative of this guy, I hold the v constant, take the derivative of the x, and then I hold the x constant, take the derivative of the v, right? So that drops down to the second power of v, right? And if I have taken a derivative, I have to pull one of those out of there. Right? So I get the L minus 1 derivative. Okay, well, let's do it again. All right, so now I'm accumulating terms here, right? And each time I take these derivatives, right, I'm going to keep going, right, until I run out of derivatives. And so what you're going to find is that there are going to be L plus 1 of those terms. All right, think about it. Here we only dropped down 2, and there are 2 terms. So 2 plus 1 is 3, right? So if I go down one more, I'm going to go ahead and add an extra term. So as I keep going, I'm going to get L plus 1 of these terms. So that is going to be, well, this is a wacky proof, I get it. So if I have 2L xv, this is going to be equal to L x d x to the L plus 1 on v plus 2L plus 1 d to the nth derivative v d xl. Right, so if you think about it, this term here that's accumulating here, the one that has a second derivative here, is one less than that, which is a third derivative. Right, so each time you go down, this term on the right is always going to be the number of derivatives that you took. So here I started and I took 1, I got a 1. Then I took another, I got a 2. And then I took another, I got a 3. So if I start with L plus 1 derivatives on this, I'm going to end up with the L plus 1 derivative of v. Right, but this one, the one that's been accumulating, this has got a derivative that's 1 less than the outer term. So here you're going to have that derivative only to the nth derivative. And so we get a really interesting equation that looks exactly like this. Okay, so what can we do with that? That's super exciting. All right, so we need another trick. Surprise, surprise. This is really cool, right? It's called Leibniz trick, right? So if I take a plus b to the nth, right? That's going to be a0 b to the n plus nab n minus 1 plus n minus 1 over 2 factorial a squared b minus 2, right? Just a binomial expansion. Okay, so now if I take that derivative of, if I take the derivative here of two functions, that the nth derivative of two functions, and I use the product rule, we're going to get the following expansion. We're going to get f times the nth derivative of g, d dx l, plus l, the partial of f with respect to x, times the d dg l minus 1, dx l minus 1, plus dot dot dot. Right, so the f term here is going to be growing by binomial expansion, right, in the number of derivatives, whereas the g starts high and then it falls off. Right? What we're doing is we're using the product rule and the binomial expansion to pull it on out. All right. Then what we can do, and this is pretty cool, right, is we can say that we can look at the following term. Consider d dx l plus 1, and we're going to take it on x squared minus 1 dv dx, right? So this is going to be equal to the nth plus 1 derivative on x squared v prime minus the L plus 2 derivative of v, right? Having taken this and applied it there on the v term. All right, now we can take advantage of this trick. We can say, well, wait a minute, let's make f equal to x squared. Well, any term here, right? So the first term here is going to be fine. The second term, well, I take the partial of f with respect to x, you're just going to get 2x. Well, the third term is going to have a second partial when I use the chain rule. So you get 2, right? But then every single term after that is going to be 0, because when I take the derivative, the third or higher order derivative onto 2, I get a 0. So I'm only going to have 3 terms here, right? Which it's still substantial, but let's take a look at it. So this is going to be x squared, right, times the L plus 2 derivative on V Hi, John.
How you doing?
Plus okay, so 1, 2, and then there's going to be a third term, right? Which is going to be plus L plus 1 over 2 factorial 2, and this is going to be dl dx to the nth power of v, and of course this term here, the one hangs off the edge. All right, so what did I do there? Sorry, it was a little chaotic there, people coming in and out. So what I did was I applied this Leibniz rule here, right? So I said, okay, the first term is going to be just the g derivative here, and I'm going to leave the x. So that's why I leave the f here. That's why there's an x squared, right? So I plug that in, right? And of course that's on the v, right? So then remember that the g here is, if the f is the x squared, the g is going to be the first derivative of v. So if I just want this in terms of v, I'm going to have to take a second, L plus 1 plus 1, so L plus 2. So this term is this second term in the binomial expansion, so I'm going to have the first derivative of f, right, so it's 2x, right, and then I have the term from the expansion, that's the n, right, so I get the L plus 2, right, and then I have just the first derivative, because now I'm looking at dg dx, but only to the L minus 1, right, so, yeah. So then we keep going with the expansion, and we have the last term there dangling off on the edge. All right, so what we can do here is just bring this puppy over to here, and we get something really cool. We get 1 minus x squared, right? Sorry, it's the other way around, right? It's x squared minus 1, right? And then I have the second derivative of dl dxl of v, right? So what I did there was I pulled out that second derivative there. So here you have plus, I have 2l times l plus 2, and you have x dl dx ddx, and then this is going to be dl dx to the l of v, all right? You're only going to pull out one derivative there. Kind of a weird thing again, right? And then you're going to have plus, and you'll have l plus 1 the nth derivative of x on v. Okay, that's weird, but look what happens. Crap, this should be a different sign here, right? Oh, yeah, all right. So you win some, you lose some. There's a sign issue. Anywho, if I call this my theta, I get the second derivative of theta, x squared minus 1, plus some constant with an x, the first derivative of theta, plus some L plus 1, theta equals 0, which is in fact the Legendre polynomial differential equation. So that says that this function right here, as wacky as it is the solution to that equation. All right. Whew. That's a mouthful. All right, so what does that tell us? And here's the important part. The important part is using this. All right, so there are a couple of different, this is going to have many different terms. So I have P0, right? That's when L equals 0. And that's going to be equal to 2 to the 0 times 0 factorial. Remember, 0 factorial is 1. I'm going to take 0 derivatives of x squared minus 1 to the 0. So 1, 1, 1, 1, this is 1. So the first Legendre polynomial is 1. Okay, let's look at P1. Well, everywhere I see an L, I put a 1. So I get 1 over 2 times 1 factorial, right? I have the first derivative of x squared minus 1. I take the derivative of that, and you get 1/2 times 2x equals x. So the first Legendre polynomial is x. All right, what's the next polynomial? P2. So you have 1 over 2 to the second power times 2 factorial. And now I'm going to have to take the second derivative of x squared minus 1 squared. All right, so now it's starting to get a little complicated. So let's think about this. This is 1 over 8, right? 2 to, 1 over 8. So I'm going to take the first derivative, and I'm going to do the chain rule. Okay. And then I'm going to do the product rule for the next derivative. So I'm going to pull out this 4 here, and you get 1/2 d dx x squared minus 1x. So we're going to hold that constant, take the derivative of the x. We get x squared minus 1. And then we hold the x constant and we take the derivative of this. So we get plus x 2x. So now let's do some arithmetic. So this is 1/2 x squared minus 1. And this is going to be plus 2x squared. Or 3/2 x squared minus 1/2. And that is the second Legendre polynomial. And on and on and on and on, all the way to infinity. So that gives me, right, remember of course that x is equal to the cosine of theta. And that tells me what my solution will be. Remember that I had the following. Remember that I had a Laplace's equation in spherical coordinates with azimuthal symmetry. Okay? And what I got out of this, which was great, was that there were two solutions. There was V r theta, and it was equal to R times R with an L times theta cosine theta with an L. And so, because there's L solutions, we can write this as a sum. It's going to look like the following. The sum of L equals 0 to infinity. So of A, L, R to the L, plus B to the L, divided by R, L plus 1, times PL cosine theta. And that is, in fact, the solution in spherical coordinates with azimuthal symmetry of Laplace's equation.